Okay, so before I start with the lecture of today, actually, I asked you to give me the feedback, and unfortunately, only there were 2 respondents. So, but I went through the feedback. The only concerning point which I saw was like students are not informed about the grading criteria of different assessment items. So actually, I have at the start of the semester, I prepared the rubric for all the assessment items, but I'm not sure whether it is visible to you or not. So I will go and double check. If it is not visible to you, I will make it visible. Okay. So, okay. Anything else other than that? No. Okay, so these slides are, I haven't prepared them. These are the slides from the authors of the paper, so which they presented at the conference. So I simply downloaded them and I'm going to present them. And this time I am going to little bit change the order of presentation. Previously, what we were doing was like we were first going through the background and then addressing the paper itself. But what I have seen is that sometimes we are spending much more time in background than on the paper itself. So let's first discuss the paper. I have the background slides also. So let's first at least discuss a part of the paper, and then I can go back to the background slides. And if you have questions, you can stop me. Okay. Okay. So the DRAM chip, it is itself is designed, it is designed in a way such that it just behaves as or it is organized as an array of memory cells, and each cell can store at least in DRAM 1 bit of data. So depending like either a value of 0 or a value of 1. And as I said, it is arranged in form of a 2-dimensional matrix. So you can consider it just like it has multiple rows and then it has multiple columns. Okay, so each cross section of a row and a column, you can consider it as a cell, memory cell, which can store 1 bit of data. So here they are using some terminologies. As I said, I will use the background slides later, so it will become clear to you what a word line is. But word line is actually a signal which you need to activate to enable reading or writing from one complete row of the memory array. Okay. So if you let's say if you enable it, then only then, if you enable the word line, only then you can either read the data out of the whole row, or you can write the data to the whole row. So here what they are saying is that, let's say if you have to, if you want to read or write to the row, so you first have to open the row, which basically mean to enable it or place the high signal on the word line. Okay. And then once you are done with reading or writing of that particular row, you close it, which basically means you disable the word line signal by placing the low signal on the word line. Now, the main idea here is that if you repeatedly read and write, like open and close repeatedly to the same row in the DRAM chip, then what happens is that you can induce errors in the neighboring rows, not in the row which you are opening and closing repeatedly, but the neighboring rows of that target row or that aggressor row. So this row is named as aggressor row, and the rows in which the errors are induced, they are known as victim rows. Okay. So repeatedly opening and closing a row induces disturbance errors in adjacent rows, and you can say like, okay, then what? So if errors are induced, then what? So, but this is dangerous. Why this is dangerous? Because these adjacent rows store the data which is used by applications. So if data becomes corrupted, then your application, your program, your operating system will not work.
So is this attack mostly just to try and cause damage or corruption to the adjacent as opposed to trying to actually like steal any information?
Yeah, this was like published in 2014, so there are a lot of many other papers which have improved on this, both in like in the direction of improving the attack and in direction of improving the defense. For example, even in this paper, they have mentioned that with a little more effort, what we can do is that instead of inducing the random errors in the victim rows, we can control what bit value you want to set in the neighboring rows, which basically means, like, let's say in the neighboring row, if you have a control data stored, and let's say that control data is the conditional variable which you are testing in a condition. If condition is true, print my debit card number. And now if you know where that condition is mapped, and if you have a mechanism where you can induce the particular values, like for example, you can set that bit equal to 1. So while actually its original value was 0, then it can become more dangerous, right? As compared to only here in this case where it will lead only to erroneous computation, like your program will not behave as it is supposed to behave. Okay. So yeah, you can make it more dangerous, yes.
So, but you're not able to target a specific bit. It has to be within the row. So it's everything in that row, and you don't know exactly which one is going to be corrupted, but one of the bits in that row would be corrupted.
Yeah, in this variant.
And this one, okay.
In this variant. Okay, so quick summary of the paper. So what did they do is that they are not claiming that we are the first one to discover that by repeatedly opening and closing a particular row in memory, we can induce errors. But what they are saying is like, we are exposing that it exists and it is prevalent in contemporary DRAM chips. Like for example, before them people have reported, but only in like fringe cases. It was not a widespread thing. They are the first to expose it in the commodity DRAM chips. They are the first to demonstrate how it's very simple program you can use to induce the errors in the neighboring chips, in the neighboring victim rows and so on. So they expose the existence and prevalence of disturbance errors in DRAM chips of today, which I said like commodity chips, contemporary commodity chips. And out of like 129 modules which they tested, they found that 110 of them are vulnerable, which basically is a very high rate, right? So what does it mean? It means like if an attacker knows this, that by repeatedly closing and opening the same row, the row which belongs to the attacker, then attacker can corrupt data on so many systems, which are like, let's say, deploying these 110 memory modules. Okay. So the second contribution is like they characterize the causes and symptoms. They just don't say that, okay, we did our experiment and we found out that out of 129, 110 modules can be corrupted. Our memory data in 110 modules can be corrupted, but they explain that, okay, what is the reason for that corruption, how it happens to occur, and what are the symptoms. So which basically is, as shown in the previous slide, the basic reason is that if you can repeatedly open or close, which basically means repeatedly read from the same row, then you can induce the errors. And not only that, they also propose different solutions, and then they like how to say, they advocate for one particular solution of like. They have proposed 7 different solutions, but then they like advocate for the final one, a solution which is low cost, which doesn't need any extra hardware support, and which can be deployed on the existing systems. So they are not only reporting a new memory attack, but they are also proposing some solutions to prevent that attack. Okay, so like in 1968, too old, IBM's patent on DRAMs, and then Intel manufactured the first commercialized DRAM chip in 1971. And they experienced that there are some malfunctionings in that particular chip, even in, you remember back, like now we can place much more number of transistors on a single chip, but back at that time, like in 1971, relatively there were much lesser number of transistors. Why? Because the size of the transistor was bigger. So if the size of transistor is bigger, the interference because of like due to the device, due to the physical characteristic of the device, they are not very significant. But as you start reducing the size of the transistor, so all these electrical effects, they become more and more prominent. So even back then in 1971, they found out that there is bit line to cell coupling. So bit line, what is bit line and what is cell? Again, when we will go to that background slide, you will see what is bit line, how it is used, and what is its function both for word line and bit line, and what is the cell. Okay. Then in 2013, they observed row-to-row coupling, which basically means that coupling basically means that the operations performed on one row in the memory chip, it can affect the operation of another row. So there is some kind of coupling, some kind of relationship between two rows. But they observed in 2013, but the earliest reported was like in 2010. And at the same time, when they were working on this paper, Intel released its patent, which mentioned the word row hammer. So they have mentioned in the paper that when this patent was released, our paper was under review. So these were like things were happening simultaneously. So coupling in DRAM is not new, and it leads to the disturbance errors if it is not addressed. So I cannot go to that side because that is not my area, because it talks about disturbance occurs because of some electromagnetic effects. The way the current flows from the devices, it can actually induce electric field and magnetic field in other components, not other components, but like if it is going through one particular channel, in the one particular channel of the transistor, so it can affect, for example, the capacitor which is connected on the outside, on the output, or it can affect the other connecting wires in the same chip which connect the other transistors. So this is like, we don't know, I mean, as a computer engineer, I don't know how in detail this works, but it is known that these problems exist. And as a result, what happens is that our transistors can malfunctions or they can misbehave. They don't show the same behavior as we expect them to show in a normal operation. Yes.
Is that row-to-row coupling side effect of something else, or was it on purpose created for improving performance?
Side effect of something else or what?
Or do it on purpose to improve performance?
No, it is side effect because, as I said, like, actually I have some slides to explain that. As you reduce the size of the transistor, so what happens that current flowing in one transistor, it can affect the operation of the other transistors, because now they are very small in size. Any kind of interference can result in a drastic changes. So this is like kind of so coupling here is not intentional. It is a side effect of the smaller size of your transistor.
And the physical medium affects the actual shapes of the transistors, right? So
Physical medium, by physical medium, you mean the substrate of like the substrate of the transistor.
Yeah, kind of. So like, for example, solar flares or solar radiation affect.
Okay. So yeah, but yes, that can happen. Like if you have solar radiation or any other kind of radiation, or you are working in a, let's say, very noisy environment, those kind of interferences can create problem. But even here, we are not talking about those external factors. We are talking about the coupling which results because your transistor size has reduced. Like now, let's say the transistor size or the technology size is like, let's say 3 nanometer, which is too small, right? So 3 nanometer mean that the width of your, the width of the channel of the transistor, it is only 3 nanometer. So which basically mean like you are packing too many transistors very close to each other. So as a result, the electric or magnetic field generated as a result of the current flowing through one transistor affects the other transistor as well in the neighborhood. Okay. So I mean, traditionally, how I mean people have tried to address the problem because it is not something new which they have discovered. So one option is that at the design time, you improve the circuit level isolation, which basically means you use some techniques to isolate one transistor from the other in such a way that the operation performed by one transistor does not affect in any way other neighboring transistors on the same chip. The other option is that once you have produced the chip, you test for disturbance errors, and then those chips which are erroneous, you throw them away. However, because in spite of these two approaches, still at the time when they were like working on the paper, they observed that still the chips with the disturbance errors, they were deployed in the systems, and people were using in their different kind of system, whether desktop or industry grade systems. So which basically mean that even in spite of those mitigation techniques, still an attacker can exploit the lower reliability of the DRAM chip to make the data corrupted. Okay. So how to induce the errors? So let's say you have this CPU, x86 CPU, and then it interacts or it is connected basically with the with your DRAM module. So let's say that what you have done now in the memory chip and in the bank of the memory chip, you have put, let's say you have initialized the whole memory with ones. All the rows contain one. And one of that particular row, you are just naming it as X. So address X, okay? So it is located at address X. So what you do is that you repeatedly open and close that row at particular address X. So, but you need to avoid the cache hits. So why you need to avoid the cache hits? Because you every time we want the rows to be closed and open. If we want the rows to be closed and open, we want to make sure that first time when we read the data, definitely it is brought into the cache. Okay. So if we want that the next we want to be closed, what we need to do is that we need to flush the data outside from the caches, and so that that row is closed. And then next time when we read it, it is again brought again from the memory into the cache. So for that, to avoid the cache hits in the next time when they are going to read it, for reading, you have to first open it. And once you are done, you have to close it. So when you are going to read, basically, which means you are going to open, before that, you have to flush the data from the cache. So which was like left behind as a result of the previous read operation. And you also need to avoid the row hits to X. Again, now this row hit is a concept which I will explain. So basically what happens is like, again, I will explain in the other slides, but here let me explain quickly. So you have these different rows. So you want to read the data. You have an output buffer, which is not shown here. So when you say, okay, read the data from X, so the whole row is copied into this row buffer, okay? But one row is very long in size, like for example, 8 kilobyte. But at a time you cannot read, it is not possible for you to read the 8 kilobyte of the data from a row in a single cycle. It is not possible. Why? Because your data bus is at most 64 byte. Okay. No, 64 bits, not 64 byte even. So what you do is like you in the row buffer, from this whole row, you get all of the data in this row buffer, and then you send back to the CPU only 64 bits. But why you are putting in the row buffer the 8 kilobyte? Because you are anticipating that maybe the next time, the next data that needs to be read also belongs to the same row. So you don't want to like go again and copy the whole, activate this row and then read it again. So basically, opening a row and closing it is expensive. So that's why what you do is that when you open it, you copy the whole row into the buffer. So next time, if the next 64 bits you want to read also belong to the same row, you can simply serve that read from the row buffer, which will be faster. Okay. And then this is known as row hit. If the second read is in the same row, you are reading from the row buffer, and this is named as row hit. Next time again, if the read belongs to the same row, there will be again a row hit and so on. But let's say next time, if you read from a different address, from an address Y, which is mapped to a different row, then there will be no hit, there will be a row buffer conflict. So which will mean that you need to pre-charge that row buffer. Pre-charge means you will need to set its voltage level to a certain value. And after that, you will then read the whole row, which corresponds to the address Y into that row buffer, which is more expensive. Okay. So what they are doing is that, okay, so we need to avoid row hits to the X. Why? Because we want to repeat, if all our reads are, what we want to do is that we want to repeatedly read from the X, okay? But we can repeatedly read from X even when we are like, let's say you say read from X, the first 8 bits, then you say next 8 bits, then next 8 bits, then next 8 bits. Okay, everything, you will be able to read all of them, but what is happening here? Your row will never be closed. Why? Because you are always reading from the same. So the data, it is whole, let's say 8 kilobyte data is in the buffer. So every time you are reading from there. Okay, you are never closing it. This is always active. This line is always active, word line. So we need to close it. So for closing, what you need to do is that next time, instead of reading from X, what you do first, you read from X, then you read from Y. So when you activate Y, this is deactivated. When this is deactivated, it means it is closed. So when you read from Y, now this will be copied into the row buffer. Okay, and again you say read from X, which means now Y will be closed and X will be opened. Okay. But our target is to repeatedly read from X in such a way that on every time we are opening and closing it. Why we want to do open and close, because we want to toggle the value of the word line from 0 to 1, 0 to 1, 0 to 1. Okay, so which will generate the activity and which will, as a result, lead to the flow of the current in the transistors, which comprise this row, and flow of the current from those transistors will induce the errors in neighboring rows. Okay, but if you are not toggling this line, not opening, closing, you are always maintaining active, it will be at a stable voltage level and no current will be flowing. Or even the current, if like this is simplistic explanation, or even if there will be some leakage current, but that will not be sufficient to induce the errors. So that's why we want to avoid the row hits. Okay, we want to read from X, but we want to avoid the row hit on consecutive reads. So that's why what they are doing is, after reading X, they read Y in another row, which will close the row X and open the row Y, and then again read row X. And for doing that, they have this simple program where what they are doing, this is written in assembly. So what you are doing, you are saying, okay, move move data from this address X. So these brackets mean that use this X as an address. So whatever is this, read data from this address and load it into the EX. Whatever is in Y, load in EBX, then flush X, flush Y, fence, and then go back to the loop. So here what you are doing, you're reading from, first you are reading from X, so this will be open, then read from Y, this will be open, then you flush both of them. Why you're flushing? So that when you read next time X, you don't get the data from your caches. You get the data from the memory. Only because if the data is served, your request is served from the cache, the row will not be opened or closed again. The data is still there in the cache. Okay. And M fence, okay, I will get back to, I will take your question. So M fence, it is required because what happens is like, so let's say this is your core, L1, L2, and then it is connected at some point with DRAM controller. Which is responsible for controlling the traffic to and from memory chip, right? Now we said, okay, we do CL flush to remove the data from caches. Okay, the data will be removed from here, but DRAM controller itself has a buffer, which is known as fill buffer. So what happens is that it is possible that data is flushed from L1 and L2, but it is still located in the fill buffer. Okay, so what happens is that next time if you want to read, your request is served from there. So that's why they are doing the fence. Why they are doing the fence? Fence guarantees that no following instruction can be executed until the data is actually written into the memory. So like it is moved from here to the memory. Okay, so that's why they are putting in the fence. And why we want to need the data we want to put the data back in memory, because we want to read back from the row. And because we want to open and close it again and again. Okay. And after that, you jump back to the loop and then keep doing this again and again. Yes.
You answered it with the demonstration. I was just wanted to clarify that CF flush was to avoid the row hits from clearing it from cache.
Okay. So now what you are doing is like, okay, yeah. So here, for example, you first go to the X, you read some data from there, but your target is to activate you are not actually interested in the data itself. Your target is only to open the row, okay? And then after that, you open the row X or row Y and read that data. And then you flush both of them from the cache hierarchy and from the fill buffer. And then you keep doing the same thing again and again, okay? And as a result, what happened that in the victim rows, you see that some of the data is, some of the bits are flipped. So these red bits, they were actually 1 and they are now flipped to 0. So data is corrupted. Okay, so they did experiment with different kind of systems. So they have like, they use 3 different Intel processors and 1 AMD processor to conduct experiment. And they found that they were able to induce huge amount of bit flips in all of the experiment, in all of the experiments. Okay. So disturbance errors are a serious reliability issue. How? I think they explain in the next slide. So why it is like, what are the implications and why we should even consider it as a problem? Because it breaches the memory protection. So the basic guarantee a system gives to the user, any program or to the application is that like no one can access your memory in any way, either in reading, either to read your data or to write your data. However, here this protection is broken. if, as we have seen in the previous program we've seen is a user level program. There are no privilege instructions. All are user level instructions. But by repeatedly running that, I can induce errors in the victim rows. And if those victim rows contains the data of another program or other user, I am breaking the memory protection. Okay. So OS page, typically 4 kilobyte, for example, it fits inside a DRAM row, 8 kilobytes. So one DRAM row is if it is 8 kilobytes, it can host two pages. Now, if the two pages are residing in the same row, it's mean they are next to each other. And now assume a situation where one page, first 4 kilobyte contain the data of a one process, and the next 4 kilobyte in the row, they contain the data of another process. So let's say this is a memory row of a memory bank, 8 kilobyte, and this 4 kilobyte, it contains the data of, let's say, process 1, and this one contains the data of process B. Now, so adjacent DRAM rows can have effect on the other rows, and it depends. Like, let's say if it is process B is a user process or a OS process, we don't know. If it is a OS process, you are in a more dangerous situation. If it is a user process, only one program of a one particular user process will not work. But if it is an OS, it can affect many multiple things. So here is this like disturbance attack. By accessing its own page, a program could corrupt pages belonging to another program. And they have shown in the previous example a very simple program by which they can corrupt the data of the victim without using any privilege instructions. Yes.
Is this exploit on the breach of memory protection, is this used for capturing actual usable data, or is it just to corrupt the neighboring rows and make them unusable?
So the first version of row hammer is only to corrupt the data, but not to like steal the data. Okay, but if you think that corruption is like acceptable or you can tolerate it, it is not true. Let's say like you have passwords stored in memory, and then those passwords are corrupted, then you are not able to recover them. And if you are not able to recover them, you may not be able to do many things, right? Okay, so I am skipping this because I don't think this is important for us. So how they build their infrastructure, the test platform. So what they do is like they have a desktop PC, and then they have the FPGA board. FPGA board is actually responsible for running the test engine. So test engine is like basically that small core program, but they want to run it at million of times. So that's why they are a million of times and on multiple DRAM chips. So what and they also like if they want to modify, that's why they are deploying it on the FPGA board, so that if they want to modify the test engine, they can do it easily. They have on the FPGA board, they have deployed a PCIe, which is actually used to interconnect your CPU with your DRAM modules. And they have the DRAM controller, which is also deployed on the FPGA. So FPGA field programming will get array for those of you who don't know like what is the basic idea. The basic idea is like, for example, if you get an Intel x86 chip, you cannot modify it, right? You cannot modify in the way like, let's say you say, okay, I want to do an improvement in this processor, but you cannot modify it, right? So FPGA gives you this flexibility that actually you can program it to behave, let's say, work first as an x86, but then you say, okay, next 1 month later, you want to say, okay, I want to work not on x86, but let's say on ARM processor. So you can program the FPGA to implement the ARM processor. Or let's say you want to implement the MIPS, you can simply program it to run the MIPS processor. Okay. So what they are doing is basically that you are actually building in hardware the DRAM controller, and you are actually building in hardware this PCIe, which is used for which is used as an interconnect with your CPU. Okay. So these are not like your software programs. These are not. These are hardware modules deployed on the FPGA. So this is like they just how they implemented in the real physical world. They have this PC and they have these FPGAs, and here so they haven't shown here the DRAM modules, but they must be interfaced with their FPGAs. And these FPGAs implementations hold the implementation of or have the implementation of PCIe and the DRAM controller. Okay, so they did experiments on DDR3 DRAM module from 3 different vendors. They didn't show their name because that can be problematic. But what they say, I said, is like these 3 companies, they have the major chunk, a major share of the chip industry, memory chip industry. So they tested total of 129 memory modules, and they found from 3 different companies, 43 from A, 54 from B, and 32 from C. So basically, what does it mean? It means that this row hammer attack, it is agnostic to the technology, or it is agnostic to the manufacturer who is developing these chips, which basically means it can be applied to all kind of chips, memory chips. And they these chips which they have tested, they were manufactured in the time period of 2008 to 2014. Paper was published in 2014. And their capacity ranges from 512 megabyte to 2 gigabyte. Okay, so in first, the memory modules from company A, they saw that they can induce errors up to 10 raised power 7 errors. So actually, instead of reading this number, the takeaway is that they're successful in inducing huge amount of errors in all kind of the memory chips from all different manufacturers with all different capacities ranging from the time 2008 to 2014. So here in this graph on the x-axis, they have like when was the module they are testing, it was manufactured. And on the y-axis, they have like how many errors they were able to induce per 10 raised power 9 cells, right? So they observed that the first time this row hammer attack can work is for the chips that were manufactured in 2010. For the chips that were manufactured before 2010, it doesn't appear to be a problem. Like row hammer cannot work. Why?
Let's talk about the size of the traces being super tight, so they're getting smaller and smaller.
Yeah. So the problem is actually coming from the density. So you're packing more and more transistors on the same chip. Why? By how? By reducing their size. And there comes a point in time or in the there is a size after which if you cross that threshold, after that your transistors start becoming less reliable. Before 2010, that was not a serious problem. And then from that point onwards, what you see is that the number of errors they were able to induce per 10⁻⁹ cells start increasing. And for all three manufacturers, yes.
Are there any other factors that affect the error rate, such as capacity or reading writing speeds, or how many DRAM parts are there in the system?
Yeah, for example, reading, writing, capacity is actually. So reading, writing speed, they have mentioned in the paper that it depends upon the speed. The faster you are able to read and write, the more susceptible the memory module is to like, you can induce more errors in that memory module. If a particular memory module can do reading, writing at faster speed. Why? Because faster speed means basically you are able to switch the transistors at a higher rate. And if you are switching at higher rate, means switching frequently, so you are, as more frequently you switch the transistors, you are, what you are doing is you are enabling the flow of current more and more, which actually results then to leads to those electromagnetic coupling effects, which they have mentioned. Capacity, it depends how you interpret the capacity. If the size of the chip is same, but you are reducing the size of the transistors to increase the capacity, then yes. If you increase the capacity, you are reducing the size, and you will lead to a situation where row hammer can be more successful. And what they have observed is that all modules which were manufactured in 2012 and 13, all of them are vulnerable. There are some cases like, okay, in 2010, 11, it first appeared in 2010, but then there are some modules which were manufactured in 2010 and 2012, but they didn't have the reliability issues. But as the time goes on, they started reducing the size further and further, and as a result, the memory modules become more vulnerable. Okay, so this is not the complete presentation of their slides. I will go through the rest of them in the next lecture. But now let me go back to the background slides. Any question? Yes.
So since Rowhammer is using the CL flush command, is it also applicable to use it with what's the one called flush plus reload attack to possibly gain information?
How the even two are related, I don't understand.
I'm just asking.
Read, flash plus reload, and row hammer.
Yeah, I'm just asking if Rowhammer is able to kind of make flush plus reload a more susceptible attack by combining the two, because
Flash plus reload is depending on the caches. Like
yes.
it is exploiting the caches.
Yeah.
And also depending upon like the same function is mapped in the address sharing, right? Page sharing.
Yeah.
So you can use CL flash, that flash plus reload attack on all kind of memory chips. Doesn't matter whether they were manufactured before 2010 or after 2010.
Yeah.
If you are asking that by combining row hammer with flash plus reload can be increased, let's say the success rate of the flash plus reload,
Yes.
I don't think so. I don't think so. Because the two are doing two different things, right? Two are doing two different things, because in flash plus reload, your target is to, let's say, steal the secret key, right? Here you are not interested in stealing anything. You are interested in corrupting let's say you are interested in corrupting the key.
Yeah, but would that not allow the attacker to gain more control access once they have the information within the system? Because if they disrupt the system, are they still not able to?
What do you mean more control to the attacker in what way? Let's say if I'm launching flash plus reload attack.
Yeah.
Okay.
Or gaining.
So if I like are you assuming as attacker at the same time I'm also doing row plus row hammer attack?
Yes, both at the same time. Well,
What if that just make the data that you're stealing unusable because it's corrupted?
So like, yes, it will make like, it will. As a whole, it will be more serious kind of attack. Definitely, if you're like, I'm launching one attack at a time. And then in another scenario, as an attacker, launching 10 different attacks. Of the same type or of different types, right?
Yeah.
Doesn't matter. But compared to scenario one, I am becoming more dangerous, right? In the scenario two. But if you say that, can we use as a result of row hammer, whether flush plus reload will be able to steal or steal more bits of the secret key? I don't think so. But can you be like slow down or create more problems for the victim? Yes. Because now you are doing, you are like attacking from two different aspects or two different angles or two different sides. Yes.
Does the row hammer attack have to be an attack? I feel like just using the computer normally, like a random part of that issue.
Okay, can you please speak louder?
With the row hammer attack, does it have to be an attack? Because I feel like if you just use a computer normally, like if you see the program accesses the same MAC address, it'll cause the disturbance error.
Yeah, it will cause, I mean, it will cause the error, but if you are repeatedly addressing the same, accessing the same address. But as I just explained, if you repeatedly keep addressing this, accessing the same address, it doesn't necessarily mean that every time you are closing and opening the row, right? So it will, in your computer, if let's say you write a loop where you say, okay, 10 million times read this address. It will not lead to any injection of errors in other rows, in the neighboring rows. Because
It's not alternating, right?
yeah, because you are not alternating, and as a result of not alternating, you are not able to close, repeatedly open and close the same row. Looks like you don't want me to go to the background slides. Okay, let me hold your questions like for 5 minutes, okay? Yeah. Okay, so in the background, in the introduction, they actually have mentioned in the first paragraph noise margin. How many of you know what is the noise margin? No. Okay, so in transistors, so this is again ideal. Ideally, what we want is like, let's say if we have a, if I have a transistor which operates in the voltage range of 0 to 5. So transistors are basically just they like behave as a switch. They are not switch, but in terms of their behavior, you can consider them as a switch. So what you do is like you have, let's say, if you give 1 as input, this switch will be closed and it will start conducting the current. And if you give input of 0, the switch will be open and no current will be flowing. No current will be flowing, okay? So, but this is 1 and 0 is logic 1 and logic 0. But in actually, when you talk in terms of like physics, so this is like some voltage which you are coding as 1. And then this is again some voltage level which you are coding as 0, right? So what we do is like we divide the voltage range from 0, let's say we have a signal, and we divide the voltage, we have the voltage range 0 to 4, we divide it at the middle, ideally. And depending upon what value of the signal we have at a given time, we interpret it as a logic 0 or a logic 1. If the value of the signal is, let's say, greater than 2.5 or equal to 2.5, we treat it as a logic 1. And if it is less than 2.5 volt, we treat it as a 0. Okay. So now in like your chips, multiple transistors are connected with each other depending upon the circuitry, but it always happens that one transistor, output of one transistor act as an input of another transistor, right? So let's say we have two transistors, let's say A and B. So this is known as gate input. I don't want to, and I cannot go to the like that low level. But let's say this is your, so it has actually different regions. So this is known as gate. Here you have source, here you have drain. Okay. So what happened is like when you apply a certain input voltage here, so this starts conducting. So what happens that here you have high voltage, so current starts flowing from the source towards the drain, and drain is connected with the low voltage or ground. Okay. So current starts flowing from the source to the drain. Okay. And that's why this is treated as an output. So if you are, let's say if you are giving a voltage less than 2.5, this will not conduct, this will become there will no electrons will be flowing here. It will not be possible for electrons to flow here. And as a result, it will become like an open switch, because no current will be flowing from here to this point. Okay. But if you give a voltage on the input greater than 5 volt, let's say, then what happens that electrons will start flowing from the source to the drain, which will behave like as a closed switch. Okay. So, and this is known as, this is now, we can consider it as output of this particular transistor. And then this output is, let's say, makes the input of another transistor, right? Now, let's say here we have an output of 2.5 volt. And according to our like coding of the logic, we can treat it as a logic 1, right? And this makes the input of another transistor. And but let's say while our current, it travels from the output to the input, some kind of disturbance happens, and which results in a reduction of only 0.01 volt of the signal of the voltage. So the voltage received here is 2.49 volt, not 2.5 volt. But according to this coding, 2.49 is what? Logic 0, which it should not be, because we were outputting logic 1. So it should also be logic 1. But since we are saying anything less than 2.5 will be treated as a logic 0. So this is known as like a disturbance. If a disturbance happens, we can have a bit flip. So actually here, what is happening here is your bit is flipping from the logic 1 value to the logic 0 value. Okay. So now let's say how we can avoid that situation, that even if there is some disturbance, we still want to guarantee that whatever we receive here is still treated as a logic 1. For that, let's say now we consider that our output voltage here was still logic 1, but the voltage value is 3 volt, greater than 2.5, right? Now, if a disturbance happens which reduces the 3 volt only by 0.01, it will still be 2.9 volt, which we can logically treat as logic 1, right? So output is logic 1, input is logic 1, right? So a disturbance of now in this case, a disturbance of greater than 0.5 volt is needed to flip the logic 1 to logic 0. But in the previous case, only a disturbance of 0.01 volt was enough, right? To do the bit flip. So high output voltage, it is the minimum output voltage on the output of a transistor that is guaranteed to be placed on the output for logic 1. So if we are saying that, okay, we are having logic 1, we are guaranteed that on the output we will have the minimum value of this V output voltage, and this V voltage input high. It is the minimum input voltage that is required to be interpreted as logic 1. So, and noise margin is what? The difference of these two. High output voltage minus low input voltage low. So for example, let's say if I use these updated values, I say that if it is a output logic 1, then we are saying that we are guaranteeing that at least 3 volt greater than 3 volt will be available on the output. And at least we want 2.5 volt to be available on the input to be interpreted as a logic 1. So that is what I'm writing here. 3 minus 2.5, so is equal to 0.5. So in our example, the noise margin is 0.5, which basically means that even if we have a disturbance of within 0.5 volt, still our signal will be interpreted as correctly in the logical terms, right? And everyone clear on this? So this is a VOH 3 volt voltage high input 2.5. So this is your noise margin high. Similarly, you also have noise margin low. So let me give you again the similar example. Let's say you have a transistor, output transistor, input transistor. Here it is outputting logic 0 with a value of 2.49 volt. But then some kind of disturbance happens and the value of the voltage increases only by value of 0.01 and it becomes 2.5 volt. Now, according to our initial coding, we are going to treat it as logic 1. So here our bit has flipped from logic 0 to logic 1. Again, how we can avoid this? By putting the restrictions that we have a maximum output voltage which is generated for logic 0. So we are saying, let's say the maximum output voltage that is generated is 2 volt, not 2.49. Maximum is like, if it is, we are generating logic 0, the output voltage will be at most 2 volt. And the maximum input voltage will be treated as logic 0. Let's say, okay, I haven't changed it, but let's say I'm assuming it is 2.499. So this is then simply the difference of what is the maximum input voltage, which is interpreted as logic 0, minus maximum output voltage generated for the output of logic 0. So if I say 2.499 and I have reduced it to 2 volt, I have approximate, not exactly 0.5 volt. So I'm again using the low noise margin of 0.5. So output low voltage, I'm setting it to 2 volt. I'm using the same value, approximately same value for both of these parameters. And as a result, I have the high noise margin of 0.5 volt and low noise margin of 0.5 volt, which basically mean that to flip a bit from 1 to 0 or from 0 to 1, you need to have a disturbance which results in increase or decrease of at least 0.5 volt. If the increase or decrease or change is less than 0.5 volt, there will be no bit flip. So having here, it means having larger noise margin is a good thing. So if you have a larger noise margin, your transistor, your memory is more reliable. But if I have a smaller noise margin, what will happen? Even like as I showed earlier, even 0.01 volt of change can induce a bit flip. So here, for example, now when transistors are reduced, in earlier times they were using, they were using like 5 volt, range of 0 to 5 volt, but it results in more power consumption. So then what they did, they reduced, since they are also reducing the size of the size of the transistor, the operating voltage they needed is also reduced. Now it is from 0 to 3 volt, and everything also accordingly is how to say reduced in size, including your noise margins, like to 0.25 volt, 0.8. But reducing the noise margins means reducing the reliability. It is now more easier relatively to do the bit flips. Okay, so this is how scaling down transistors affects the noise margin and reliability. Yes.
Is it more expensive to have a higher noise margin?
Is it more expensive to have higher noise margin? How you measure the expense, it depends upon that, whether you depend upon like measure as a dollar value or as like power consumption.
No power.
Okay. Who wants it?
It would be because there's more fluctuation from 0 to 5 and 0 to 3. Every time you're spiking to 5, you're consuming more power than you would to alternate.
Yes. So yeah, so when you have like total operating range of the voltage from 0 to 5, one thing is clear, you have to give the higher supply voltage, one thing, right? Like here it is 3 volt compared to the 5 volt, right? Second, your signal when it is like, let's say, changing from the bit value is changing from 1 to 0. So it will be like current is flowing from 5 volt to the 0 volt, which basically means that there will be more current flowing. More current flowing means there will be more power consumption. So having, yes, you can have higher noise margins, you can increase the reliability, but it will increase your cost in terms of power consumption and also in terms of like dollar amount. Okay, so all these slides, I know I will not be able to cover them, but all these slides after this one, they are from Professor Onur Mutlu from ETH-Zurich. These are not my slides. Yes.
Something that I was wondering is if there's, so far we've done over like row hammer and then flush, because we both use the CL flush command. If that command is used for these attacks, why is it underprivileged on x86 architecture? But why don't they make it require like having privileges to run it if there's known
Okay.
vulnerabilities with it?
Yes, so now I think they have made the changes. I think they have mentioned in Flash Bus reload paper, I already cut this paper. They have made the changes like where now you can you still use the CL flush, but you can use the CL flush only on your own data, like the data which is mapped in your address. You cannot use the CL flush on any random address. So if you have access, like legal permission to access a memory address, which basically means that the address, you are the owner of the data as a program, only then you can use the CL flush. But if that address is not accessible to you, then you cannot.
So that would work for the flushing, but wouldn't that still make these attacks? Because you're only
Yes,
flushing
it
your
will-
own data.
Yeah, here they are flushing their own data.
So
yes.
why don't they make it so that's just not like an attack people can use? Like if you have a built-in cloud.
So you are saying why they even allow CL flush in the first place,
Mhm.
right? Okay, anyone who want to answer? Consider like you have persistent memory, for example, or where you want, even if it is not persistent memory, what you want to do is that you want to maybe it will make more sense if we assume the persistent memory. So persistent memory is the case like it is different from the volatile memory in the sense that the data you place in this memory, even if you remove the power, the data will still stay there. In volatile memory, that is not the case. If you remove the power, the data is lost, right? So let's say I have this simple program. A is equal to 1, A plus plus, B is equal to A plus 1, right? What do you expect, how the, like, well, at the end of the program, what you would expect is the result of value of B. 1, 2, 3, right? Okay, but it is not always like things, instructions are always not executed in order. We know that, right? So we have out of order execution. Okay, so now let's say that you have A is equal to 1. So this, let's say this is your cache, right? And here in cache, you are definitely in memory, you also have A, but you have a copy of that in cache. So A is equal to 1, right? And then A is incremented, so it becomes 2, right? And then B is also here and here. So B is equal to 3. But due to out of order execution, it is possible that B is written in the persistent memory before it, right? Right? So let's say A still here has 1, while the correct value of A is 2, right? But it holds the old value. Now, if B is written before A in the memory, what will be the value of B? 3, right? Now, let's say a crash happens. Okay. And we know that data in persistent memory is never lost, but data in the caches, it's gone. Okay. If value of A is equal to 1, should the value of be 3 or not? Is it consistent to say that value of B is 3? Because B is what? A plus 1. So if A is 1, then A plus 1 is equal to 2, but this is 3. Right? Now, you will be wondering how it answers your question, that why even CL flush is needed, right? So what you do is, here you put CL flush. Not only CL flush, but you also need fence. And you provide the address of A, and after that you say fence. Now it guarantees you that this A will be first written into the process, so this cannot happen. So A will be first written here, and then after that you will be able to do this. Now even if crash happens, your data is consistent. So that's why you need this is one example that why you need the CL flush. Why they still allow the CL flush. Okay.
The noise margin that you mentioned, is it static or dynamic? Because I assume if we're using more resources in the computer, we need more energy, and thus we need more larger margin.
Your question is correct, but your reason for having dynamic noise margin is not correct. Your hypothesis or your question that is there a situation we can have the dynamic noise margin? Yeah. Not for resource consumption, but actually to conserve the power. So there are systems which do the dynamic voltage scaling, DBS, dynamic voltage scaling. So what they do is that at the runtime, they set the supply voltage depending upon the required power consumption from like they can change from 5 volt to 3 volt or to some other higher upper bound. So if you do that, if you dynamically at runtime, you can change the supply voltage. So it basically means you are also dynamically changing the noise margins. So which means that at the runtime, your reliability will also be affected. Okay, I know I'm running out of time. We can extend 10 minutes after 4:15 for the submission, but let me use these 5 minutes to explain this, whatever I can cover. So this is how as a programmer, we use the memory. We simply say, store some data into the memory by executing store instruction, and then we say, okay, load some data from the memory into the register by executing the load instruction, right? If I have no idea of I'm a programmer, I know nothing, I know only C++, Python. I have no idea about the architecture. This is how my understanding of memory is, right? So what is an ideal memory? For ideal memory, we want that it has 0 access time. It can load and store the data in 0 time without any latency. It has infinite capacity, and it has 0 cost free, and it has infinite bandwidth, which basically means that it can transfer the data to and from. We can transfer the data to and from the memory chip in 0 time. Like bandwidth is, for example, how many bits you can transfer in a unit time. Infinite amount of bits in a given unit time, and it doesn't consume any power or any energy. But that is not possible to have, right? But that is ideal. Okay. So we want to efficiently store large amount of data in the memory, and this is how our memory looks like. It is just an array of cells, memory cells. We give an address, which is n bit, and it gives us data, which is m bit. The data arrow you can see is bidirectional, which basically means we can write the data to this address, or we can read the data from this address. So it stores the data, and it has the address selection logic because it has multiple arrays. So based on the address, we select from which particular row of those, or which particular, as I said, it is a matrix. So which particular row we want to read or write from. And readout circuitry, it is not like that you have the data directly coming from those rows on the output lines. There is a in between, there is a circuitry like multiplexers and row buffer, which is not shown here, which is also used to put the data before putting the data on the data bus. So an m-bit value can be read or written at each unique n-bit address in this particular case. So we can access all the values, which basically mean all the rows and in the chip, but not at one time. We can access them over time. Like at a given time, we can access only n number of bits. So why we are putting this restriction that we can access only n number of bits at a given time, and let's say in a single cycle, why we can't access, let's say I'm making up some number, let's say 64 bits. Why we can read only 64 bits at a given time and not 128 bits in a single cycle? Because if you want to read more number of bits at a given time, it increases your cost. Because it means you on the output, on the chip, you have more output pins and you have larger internal circuitry, and your signals are the wiring connections, they become longer and longer. As a result, it takes longer time for the signals to travel across those wires, and it becomes slow. Okay, let's stop here and try to go through these background slides before the next lecture. They are, I would not say like self-explanatory, but at least you can understand some of them. And if you cannot, there is lecture of Professor Onur Mutlu on the YouTube with the name of Memory Organization, exactly explaining these slides. You can go and watch them. Because in the next day, I want to focus on the paper itself. And if there is some time left, I will try to come back to the background slides. Any questions? Yes.
I have one question from earlier. We might cover this next lecture, but is there not a simple solution to the causing this interference, having a checksum for each row in DRAM, where when you before write or read, you checksum the bits and say, oh, does this match the previous line?
Okay. Yes.
Well, I was actually gonna ask the same question, similar to that, but it's with implementing error correction codes in the actual, DRAM, that would be a solution for that, because even if the bits do flip from the alternating currents, the, error correction code would just flip them back.
Okay. So first thing, let's come back to checksum. How you can cut the checksum? If the checksum you are storing itself in the memory, right?
Yeah.
What if I induce errors in the checksum? Right?
Yeah.
So then you cannot, one thing. Second, if you are storing the checksum for every row, you are reducing your effective capacity. I will not say exactly by 2, but let's say roughly by 2. Okay. And then on top of that, so first thing, it will not work because we can induce errors on the checksum. Second, we are reducing the memory capacity effectively by half. Third, you are doing extra memory accesses to put the checksum in the memory when you're storing the data, and reading it again when you are reading the data, to reading it again for comparison. And then again calculating the checksum on your processor and then doing the comparison. So you are adding too much cost. So even if you have zero cost to learn. One thing. There were no reading notes for the last week, right? Some of you submitted the reading notes. Okay, I think there is an online student who submitted it. So I canceled those reading notes. There will be no reading notes, and the weightage of those reading notes, I'm thinking to like evenly distribute it for the remaining reading notes from this week onward. Is anyone fine with that? Is anyone who is not? There was no reading note for the last week, but in our initial syllabus, we said that every reading note has a 2 absolute points. So what I'm proposing is distributing the 2 absolute points of that reading note over the remaining ones.
Yeah.
Fine, everyone?
Yep.
Christian, right?
Yeah.
So I sent you a message.
Yeah.
Yeah, are you responding to that?
No.
Or if I distribute your words for the remaining.
That's right.
Okay.
Thank you.
And I think you also a message.
Oh, yeah, no, yeah, that's fine.
So you want to, is it fine if I don't grade your?
Oh, that's true.
Okay.
So is it fine if,
I also said,
yes, is it fine if I do paper 5? Cause I already started that last week.
I'm fine with that. I mean, I just want you to confirm which one you want.
Yes, okay, yeah, send up the follow-up email on that.
Okay.
Demetrius coming tomorrow to the meeting.
No, watch, he's not going to understand, like, it is only between the two people. It is only like 5 years.
So I just wanted to check whether he is also working on the same thing or I have.
Listen, I earlier tried to like clarify it to you. I just want him to get experience with their file and if possible, to replicate SSE. Okay, but that is not research.
Yeah.
SSE is already there, people have published it, and people have reported the results, right? And actually I want to just like use, benefit from him to, in a way, if it's possible, to speed up the work on the project.
Yeah,
So that's why I asked him if he can look on the workloads and see how he can run the Redis. So let's say if he is able to successfully run the Redis on his machine. I'm not talking about Java, on his machine. So at least he will get some experience with that, which he can share with you.
Yeah.
Okay. And as a result, it will possibly save some of your time. Okay. So
Yeah, now I'm clear. So why I asked is like, if he is also like replicating the same.
it doesn't make sense. Why would I ask two students to do the same thing when it is like wastage of my time and time of students?
So is he working in this, or if I want to contact him? So is it through only Teams or will he be available in this Sensor building?
You can contact on the email. You have a email, right?
No.
So you can contact on the email.
Okay, no, if I wanted to check whether if he is available physically in the campus. So okay, so